This is video 29. In this video, we introduce a specific kind of path assembly called fork. A fork is built from segments of another path assembly P. It is a useful tool to find a pumpable candidate segment in the path assembly P and to prove the shift lemma. We start by giving a definition of a fork. Consider a simple path assembly P producible by a tile assembly system. The seed is in black. Consider two indices I1 and I2 such that the segment of the path assembly P from index I1 to index I2 is a candidate segment. Let V be the direction of this segment. Consider the segment of the path assembly P from the index I2 to its last tile. This segment is in red. Let's try to translate this segment by -V. Here, the translated segment is in blue. We are in a special case where this translation creates a producible path assembly. In this case, the shift lemma is true. Unfortunately, doing this translation is not always possible. Now, consider both the original segment of the path assembly P in red and its translated segment in blue. Remark that these two segments intersect. This intersection is in green. Since the tile assembly system is deterministic, these two path assemblies are consistent. Later, we may not be able to translate the red segment by -V, but we will always be able to translate a part of it in order to create the green intersection. If these path assemblies are consistent, then we can consider the new segment in green. This green segment is in hybrid between the blue and the red segments, that is to say between the path assembly P and its translation by -V. Sometimes, this reasoning can be repeated several times to obtain a lengthy path assembly which is in hybrid between path assembly P and its translation by -V. We call such a path assembly a fork. More formally, a fork F is a path assembly which satisfies three conditions. The first one is that the concatenation of the segment of the path assembly P from its first tile to index I1 with the fork F is a producible path assembly. The second one is that the concatenation of the segment of the path assembly P from its first tile to index I2 with the fork F translated by vector V is a producible path assembly. The third condition is that the fork F is made of the concatenation of segments of the path assembly P and its translation by -V. We will try to assemble a fork in a very specific setting. We now describe precisely this setting. In the following video, we explain how to build a long fork. Consider an exposed path assembly P producible by a tile assembly system. Now consider two indices I1 and I2 such that the segment of the path assembly P from index I1 to index I2 is a visible candidate segment. By definition of a visible candidate segment, the tiles Pi1 and Pi2 are both visible from the west, not hidden by the seed, directed to the north, and in this example, they exits to the north. Now consider the direction V of this candidate segment. Since the index I1 is lower than the index I2 and since the tile Pi1 is directed to the north, and we have shown that the ordinate of the tile Pi1 is lower than the ordinate of the tile Pi2, then the ordinate of the vector V is strictly positive. This property is fundamental in most of the future reasoning. Since the tile Pi1 is visible from the west and since the last tile of the path assembly P is visible from the east, then we can define the window W associated to the segment of the path assembly P from index I1 to its last tile. This window is in gray. Let the graphs G1 and G2 be the cut of the grid associated to the window W. We remind that the graph G1 is by definition the left side of the window W. In this special case, the graph G1 is called the free zone F. Here the free zone is hatched. Also remark that the position W0 is occupied by the tile Pi1, the position Wn is occupied by the tile Pi2, and the position Wm is occupied by the last tile of the path assembly P. We remind that the tile Pi1 is visible from the west and directed to the north. Then by our local reasoning, it is possible to prove that the tile Pi1-1 does not belong to the free zone. For the sake of contradiction, Suppose that there exists a tile in the free zone which belongs either to the seed or to the segment of the path assembly P from its first tile to index I1-1. Then either the tile PI1 is not visible from the west or is hidden by the seed. Either the path assembly P is not simple or it has more than one tile in common with the seed. Either the last tile of the path assembly P is not visible from the east or hidden by the seed. All cases led to a contradiction. Thus the free zone is devoid of any tile of the seed or of the segment of the path assembly P from its first position to index I1-1. Thus any assembly of the free zone coherent with the tile PI1 is producible. We have found an area where assemblies can be built without fearing inconsistency with the beginning of the path assembly or the seed. Now, we focus on the tile PI2. This tile is visible from the west, thus none of the position west of the tile PI2 belongs to the window W. Thus all these positions either belong to the free zone or none of them belong to the free zone. Consider a position west of the tile PI2 such that its abscissa is lower than the minimum abscissa of the path assembly P. Since the ordinate of this position is greater than the ordinate of the tile PI1 and this position is on the west side of the window W, thus all positions west of the tile PI2 belong to the free zone. A corollary of this remark is that the ray starting at the position Wn and going west splits the free zone into F-NF+. In our example, this ray is hatched. In particular, consider two indices J1 and J2 and a path which starts in position Wj1 and ends in position Wj2. If index J1 is less than index n and if index J2 is more than index n, then the path intersects with the hatched ray. In this example, the intersection is denoted by a red dot. Finally, we explain what kind of fork we aim to assemble. Firstly, we are looking for a fork F which belongs to the free zone. Secondly, we want that either the last tile of the fork F is east of the last tile of the path assembly P or that the translation by V of the last tile of the fork F is east of the last tile of the path assembly P. Such a fork is called a long fork. Since the first position of a fork is always the position W0, then a long fork must go around the segment of P from index I1 to its last position. In the following video, we explain how to build such a fork.